Any other questions? I was trying to get my camera working. All right, so let's kind of pick up where we left off then. And so we had left off on POH. And so now let's take a little closer look at what POH means. And so this is just another way to show how basic or acidic a solution is. And so the POH, the formula looks very similar to the pH formula. So POH is just equal to the negative log of your concentration of hydroxide ions. And so, of course, if you know the POH, we can determine the hydroxide concentration as well. So just doing some math, you can start from here, just take both of these to the 10 power. And so then you get, if you have the POH, you can plug into your calculator 10 to the negative power of whatever your POH is. So for example, for water, and let's just pull out our calculator. So if we know that the POH is 7, then we can plug in, so of course 10 to the power of negative 7, and that's going to be our concentration. And so now in this case, right, the scale's a little flipped. So now if the POH is less than 7, that means that it's basic. And so you can compare that to the acidic scale. So, right, we had said that 7 to 14 was basic on our pH scale, and now it goes the exact opposite from 14 to 0 for POH. And so now anything less than 7 is considered basic. 7 is still, of course, neutral, and now anything greater than 7 is acidic. And so yesterday we had mentioned, or Monday we had mentioned this relationship of pH plus POH equals 14. And so, of course, you can see that relationship reflected along this scale as well. So all these add up to give you 14 along the way. And again, for our purposes, we'll just assume that we're always at 25 degrees Celsius. And the Kw constant doesn't really deviate too much from this, you know, with temperature. But again, we'll just focus on this for our cases. And so all this is a quick derivation for how it was determined. And so we had said that we had our Kw product constant. So that was the concentration of hydronium times the concentration of hydroxide ions. And that was always equal to this number, again at 25 degrees Celsius, or for our purposes, it's always equal to this number. Then if we take the negative log of both sides, so this separates out. So of course the negative log of hydronium is equal to pH, negative log of hydroxide equal to POH, and then the negative log of this gives us to 14. So right back to that formula. And so right now you have these two different methods to figure out your either hydroxide concentration or pH. And the kind of nice thing about this is, right, you can go around circular, check your answer, get it different ways, and it should all check out. So now let's look at buffers. So you probably saw buffers in lab. So you made your buffer, kind of tested the pH, and hopefully it was pretty resistant to pH changes. And so, of course, the components of the buffer, it works by either neutralizing the acid or the base that's added to the buffer solution. And so the key part of how to make your buffer is that you either have to have a weak acid, and then, of course, its corresponding conjugate base, or its weak base, and therefore its conjugate acid. So in your blood, so it's a buffer system like we mentioned. So we have our carbonic acid, and then our hydrogen carbonate ion as the conjugate base. So this would be your buffer solution. And so let's look at another example of how you make a buffer solution. And so an acidic buffer solution must contain significant amounts of both weak acid and its conjugate base. And so let's say you wanted to make a buffer based off of acetic acid. And so that's where you have to figure out where the conjugate base is. And you can think about that. So whatever your acid is, so again, in this case, acetic acid. So that's our acidic proton. And then, so we know in solution, it's going to dissociate to make H+, plus, of course, our conjugate base here. So now this is our conjugate base. And then because this is our conjugate base, we want to pair acetic acid with the appropriate base. And so in this case, they picked sodium acetate, but it doesn't matter too much what this salt is in front as long as it's a neutral salt. And we'll go over what all that means. But, you know, we could have also picked like potassium acetate. That would have been appropriate as well. Or some sort of other, you know, lithium acetate. As long as it's a neutral salt. And then you mix these two together, and so that gives you both components. So you have your base, which can either neutralize some acids, so it would react right to reform your acetic acid, or your acetic acid reacts with your base in a neutralization reaction, and then would form your conjugate base salt. So you can kind of see how it reacts, and then they go back and forth, kind of keeping things in equilibrium and keeping the pH relatively the same. And so now we're just looking at this into more detail. So what happens to a buffer solution? So we're looking at an acidic buffer solution. So we can still look at our acetic acid. So what happens when a small amount of strong base is added? So of course, again, as long as you're not overwhelming the system completely, doing like a complete neutralization, then they'll be able to buffer. So of course, this is just our acid-base reaction. So our double displacement, so we make water and then the corresponding salt. And so notice what that salt is. So that salt is our sodium acetate, which is our conjugate base again. So there's our conjugate base. So that is good. And then so the pH will slightly increase with the addition of the base, but again, it should not be too significant. And so as long as the amount of sodium hydroxide is less than the amount of acetic acid present. So, you know, again, obviously you can overwhelm your buffer solution and just completely drown it out, and then it's irrelevant. And so conversely, so what happens to our buffer solution when a small amount of strong acid is added? And so now we have, right, this reaction. So HCl plus, and so instead of reacting with our acetic acid, right, it's going to react with the conjugate base component. So you can write your new neutralization reaction. So the acid plus our conjugate base salt. So now it's going to react with the sodium acetate. So we do our double displacement reaction again, and so this time we get sodium chloride, and then we reform our acid. So we reform our acetic acid, and again, right, so then that acetic acid can, of course, always disassociate, and again, keeping our pH change at least very small. So we would expect a slight decrease, again, adding some acid, making it slightly more acidic, but again, it's going to buffer out. And again, you can obviously overwhelm it if you put a large amount and completely neutralize it, but otherwise the pH should be small. And so we can apply Le Chatelier's principle then to these buffer solutions. And so all this is saying, so we have our acid component reacts with our base to make our conjugate base plus water. And then from there, so this is just addition of base, addition of acid. So again, same thing. Now the acid will react with the conjugate base, reform our weak acid. And so in this class, we're just going to take a simplified approach to calculating pH. So if you were to take like the 200 series of chemistry, things get more complicated. But we're going to take kind of the abbreviated approach to this. And so I would write this down somewhere. And so this is for our buffer solution. And so the pH is equal to the pKa, which we'll go back and discuss this. So we kind of mentioned this, plus a log of our base over our acid. And so right, your base is going to be that conjugate base salt, the concentration of that. So for example, like the sodium acetate. So you would put in the concentration of your acetate ion versus the concentration of your acid on bottom. So of course, again, in the case we've been looking at, that would be acetic acid. And so you might see another version of this equation. So personally, I like this form more. It's just what I'm familiar with. So, and I'm used to always putting base over acid, but you might see it as pH equals pKa minus the log of acid over base. And so just know that it's the same thing. So exact same formula, use whichever one you feel comfortable with. So again, now with the negative sign, the acid is on top, so you put your concentration of acetic acid on top, conjugate base on bottom. Either way, you get the same answer. And again, so what I was kind of saying, so this equation calculates pH of a buffer from the pKa and the initial concentrations of the weak acid and salt of the conjugate base, as long as the X's small approximation is valid. And all this is saying is we have a small change in molarity, so we're not doing anything too crazy. And for your purposes, again, this will be all you need to know. So if you want to learn more about this X's small approximation and when it fails, join us in 200 level chem, and then you can do lots of math. All right, so let's go back to what's the pKa again. So we go back to this section. So now we can understand better what was Ka and what was pKa. So remember, Ka was just that equilibrium expression for acids. And so again, this is just telling us kind of the relative strength. But now this should look pretty similar to our log formulas. And so the pKa is equal to the negative log then of our equilibrium expression. So let's just check that out. Let's do phenol here just because we're looking at it. And so, you know, if you're ever on an exam or you're asking Google for things, you can figure out what to do no matter what number you're given. So if you're given for phenol, so let's say you're just given that the Ka, so our equilibrium expression is 1.3 times 10 to the negative 10. So if you want to calculate the pKa, then you just have to plug that number into our log. So negative log of 1.3 times 10 to the negative 10. And so that gives us our Ka back out. So 9.89. And so that rounds to the same thing, 9.89 there. And so again, you'd have to either be given one of these two values to solve for your buffer solutions. And then of course, you know, just remember that these buffer solutions and the pKa and Kas only apply to weak acids and weak bases. All right, so now I feel like this is kind of the trickier part for students, but if we go through it slowly, I think you'll be okay. And then ask questions. And so now we want to classify salts then as acidic, basic, or neutral. And so let's first read what it says, and then we'll digest it and break it down. So it says, if the salt cation is the counter ion of a strong base, and the anion is the conjugate base of a strong acid, neither ion reacts with water to affect the pH. Therefore, a neutral solution will be formed. Okay, so let's dissect that. So first it said a salt cation is the counter ion of a strong base. And so that means, so let's look at sodium here. So what base is sodium derived from? What base is it with? Na. But what would be like the base though? Like what's that compound that usually has sodium in it, but then it's a base? And like what's a base? So what defines a base? What's that going to be paired with sodium? I know you guys knew it. So what defines a base again? So it does take in protons, but then what else does a base do? What's like this? Yeah. But what's the base? But then like what else does it do? Like the basic definition as a base theory. All correct, but so we're comparing it like the salt of hydroxides, right? Because usually a base means that it makes hydroxides. So then all this is saying is pair it with the strong base. And let's make some space and draw this out. So we're looking at, no, I was just trying to, so you want to analyze like sodium hydroxide, it's what it's saying. So, right, you take your cation, and then if it's the counter ion of a strong base, so then you're asking yourself, is sodium hydroxide a strong base? So then, is it a strong base? So yes. So if it's a strong base, that means that it can't reform, right, in equilibrium. And so all this is saying, if it's a strong base, so sodium hydroxide, oops, I didn't mean to put that charge there, disassociates completely. And then that means that this hydroxide is not going to come and reform and grab a sodium or anything. So it's not going to do that. And so that means that in this case, right, our sodium is neutral. So does that make sense? So our sodium can't do anything. And let's see if we go back. Where's the other chart? Oh, it didn't. So right, there's no sodium here either. We just have hydroxide, and so it's just paired with water. So it's not going to do anything. So now we know sodium's neutral. So it's not going to create an acidic or basic solution. And then if we look at the second half of that, so then it says if the anion is the conjugate base of a strong acid. So now you look at your chlorine. So what acid is chlorine associated with? Yeah. Yep. So you just compare. So now we're looking, so you want to see chlorine, so it's derived from HCl. So we know HCl is a strong acid, and so all that means, again, that its equilibrium lies all the way to the right. So chloride cannot go and reform HCl or anything, and so that makes chloride neutral as well. And since our sodium's neutral, our chloride's neutral, that means that sodium chloride is overall neutral. And so let's do the analysis for these other two compounds, just so you see. And so let's do calcium nitrate. So now we're looking at, so calcium nitrate, so then we can start, let's analyze calcium first. So what base is it paired with? What's the base form with calcium? Oxide, or what was this one? Yeah, so same thing, right? Calcium hydroxide, that's the base that it's derived from. And then is calcium hydroxide, is that our strong base, weak base? So strong, exactly, so it completely disassociates. And it makes two equivalents of hydroxide. We should probably talk about this as an aside for something else. But, okay, so now we see, okay, well, calcium's not going to reform anything. It's not going to make the solution acidic or neutral. So, I mean, acidic or basic, so that means our calcium's neutral. And so now let's look at nitrate. So what acid is nitrate derived from? Yep, so HNO3, so nitric acid. And then, so is that a strong or a weak acid? Strong, exactly. So again, complete disassociation, equilibrium lies all the way to the right. So we know that this nitrate can't do anything. And so that means our nitrate is also neutral. And since they're both neutral, now we can say, okay, our calcium nitrate then is neutral. So now let's do that last one. So potassium bromide. So what base is potassium associated with? Yeah, so then that would give us potassium hydroxide. And then is potassium, yeah. Not always, but most of the time when you're looking at like these, especially group 1, group 2, then those are always like paired. But then we'll look at, you know, other situations like ammonium or acetate. So then we could have different options. And so again, this one would fully disassociate. And so in that case, that means our potassium is neutral. Then we look at the bromide. So what acid does it come from? So HBr. And so that's our strong acid. So again, lies all the way to the right, not going to reform any HBr. So our bromide salt is also neutral, making, of course, KBr overall neutral.
So both of them have to be neutral for it to be neutral?
Yes.
One of them's acidic, another one's neutral, or would be acidic?
Yes, and so we'll look at those cases, and then we'll look at what if one's basic, one's acidic, what do you do? Question?
Well, it was kind of like hers. So it's neutral if they're both neutral, or just one?
Yeah, so they both have to be neutral. So you have to analyze both the cation and the anion. So now let's look at our next scenario, and again, we'll read it, and then we'll kind of interpret it. So if the salt cation is the counter ion of a strong base, okay, so that's telling us that our cation is probably going to be neutral, right? That's all that first statement is saying. So our cation is neutral, and then it's saying the anion then is the conjugate base of a weak acid, okay. So that means that the cation is neutral, like we're starting to learn, and that would make the anion basic. And so let's go through these, and we'll start with sodium fluoride. So do your analysis again. So we have sodium. So what base is this from again? So hydroxide, so our sodium hydroxide. So we know that our sodium is neutral at least. Sorry. You know when you get like tickle in your throat? Then we have to look at our fluoride. So what acid does fluoride come from? Now I'm dying. Sorry. So now we have HF. Now I'm going to just die, apparently. And so HF, we know, is a weak acid. And so we have that equilibrium. And then, so now we're saying, well, if we have this equilibrium, then that means, right, fluoride can go ahead and accept. So now, what is it going to do? So let's think about this. So fluoride plus water, because now you're just adding the fluoride salt plus water. And so we do have equilibrium, and so that means it can react with the water to reform HF. But then what's our product? Yeah, OH minus. And so now this is telling us, so if it's going to make acid, but then we're going to get base, so now this means that our fluoride salt is basic. And so if we go up, that's what it says here. So just recapping, our cation is neutral. The anion was our conjugate base then of our weak acid. So it's going to react with water then to make HF, leaving hydroxide ions. Then we said, well, the definition of a base is anything that produces OH ions. And so now that means our fluoride salt is basic. And of course, if the cation is neutral, that means that our overall sodium fluoride is basic. So now sodium fluoride is basic. And again, so note your anions tend to be either bases or obviously neutral, and your cations tend to be either acidic or neutral, again, for the most part. So let's go through the next example. So now we have calcium acetate. I guess I'm just going to be really irritated for the rest of class. So now calcium acetate. So we can perform the same analysis. So we'll look at calcium. And of course, as you go through these, right, they start to go a little faster. So we know that calcium came from calcium hydroxide. So we established before that calcium then is neutral. Now we can analyze our acetate. So what acid did acetate come from? Yeah, and then what's the acid though? Because this is acetate. And then remember what the...
Is it like C2H4O2?
Essentially, yeah. So that would be the correct formula. So I would just stick the H in front of it. So HC2H3O2. And so remember that's our acetic acid. Go back. Let's see. Where's that chart? So this chart kind of helps you too. So acetic acid kind of reminds you what's going on. Okay, we have equilibrium. This is the acid it came from. And so, of course, this means in solution then, so we have our acetate ion plus water. Well, we said that since we have equilibrium, this can go ahead and reform our acetic acid. And then in the process, again, also create a hydroxide ion. And so that means our acetate is basic. And with that being basic, so of course that makes calcium acetate a basic salt. So back to our buffer over here. So again, that would have been another appropriate choice for this buffer solution with our acetic acid. So they picked sodium acetate. We could have picked calcium acetate. And again, as long as that salt, the cation, was neutral. So then this last one, so potassium nitrite. So potassium, we established earlier, that's from potassium hydroxide. So again, that was our strong base. So that makes potassium neutral. And then what acid is nitrite from? This chart might help you too. It has some of them.
Like nitrous acid?
Yes, exactly. So that's why I like this chart, so then you can spot, there's NO2, there's the H in front of it. We know what acid it came from. And so it's from nitrous, except so we know nitrous has equilibrium now. And so in solution, we have our nitrite plus water, right? It's going to remake our nitrous acid and then give us hydroxide again. And so, again, we can tell this one is basic. And so let's look at the last scenario. And you can tell by the example here that there's not too many examples. And so now it says, let's break it down. If the salt cation is the conjugate acid of a weak base, okay, so if it's the conjugate acid of a weak base, so that's probably telling us that the cation is going to be acidic, but we'll look at that in detail. Then it says, and the anion is the conjugate base of a strong acid. Okay, anion is the conjugate base of a strong acid. So we established that that means that it's neutral, right? And so that leaves us then, that means the cation will be acidic, the anion is neutral, and we'll get an acidic solution. And so let's look at that analysis. So ammonium chloride. So now we look at ammonium. And so this is where it could get tricky. So what base is ammonium from? So NH3, excellent. So NH3 plus our H2O gives us ammonium plus hydroxide. And so now we look at the reverse of that. So NH4 plus water. And so now, right, the water can go ahead, and I'm sorry I didn't draw this all out more explicitly, but I'll pluck off one of those hydrogens, reform our ammonia, and then leave us, so what's our product then? What's our other product? So H3O, exactly, our hydronium, and so because it formed hydronium, we know that it is acidic. So again, that's our definition of acids, something that makes H plus or hydronium ions, so now acidic. And then let's just do the analysis for chloride. And so like we've established, it's from HCl. We said previously that's a strong acid, so we know that chloride isn't going to do anything. And so that leaves us with our overall strength. So this would make it an acidic salt. And so the other scenario here, so if you have these metal ions, so the other thing is, so these metal ions can be acidic, and so they will also form an acidic solution, and especially if the anion is a conjugate base of a strong acid. So of course nitrate we established was neutral, and so aluminum tends to be acidic. And so now the last little scenario that may come up with is, well, what if one of the salts, what if they're both acidic or basic? So let's go through this analysis before we read the text. So we're looking at ammonium fluoride, right? You do your analysis. So we look at ammonium, and so we look, okay, well, this is going to be acidic, and let's just rewrite the reaction. So that makes our ammonia plus hydronium. Okay, so that's acidic. And then fluoride, so HF, we said that was our weak acid. So then fluoride will reform HF and leave us with hydroxide. So now it's basic. So now, well, what do we do? And so now it says, so if the salt cation is the conjugate acid of a weak base and the anion is the conjugate base of a weak acid, the pH depends on the relative strength of the acid and the base. And so what you have to do is compare their Ka and Kb values. So let's go through that. So it says HF is a stronger acid than ammonium, and so the Ka of ammonium is larger than the Kb of fluoride. Well, let's look at that. And so so here's HF. I was looking for, might have to Google ammonium, which is annoying, but it happens. So we look at HF. So from this is the forward reaction. So we're looking at the Ka here. And so now if we go back, and so we need to, so if this is the basic component, we have the Ka So we have our Ka of HF. And so that was 6.8 times 10 to the negative fourth. And so let's ask Google what ammonia, let's see, Kb value. All right, and then so another relationship, so you probably won't be asked to do this on the exam because it is a little tricky, but you can relate, so Ka times Kb is equal to our Kw, and so again, we need the Kb in this case because the fluoride is basic. And so we could solve for Kb. So then our base component is now 1 times 10, negative 14, divided by this. Oops. And so that gives us our Kb strength. So again, going in the opposite direction now. And so 1.4 times 10 to the negative 8. Oh, I don't know why I wrote negative 8. Negative 11. So that's, and you could also look up this value. Sometimes Google will give it to you. It just depends on like what you're looking at. And so asking Google for I asked it for the Kb of ammonia, so now we have to look at the ammonia. So I was looking at the Kb because usually a base will give you the Kb value, and that's 1.8 times 10 to the negative fifth. And so that would mean our Ka is the opposite, so, or not opposite, but we have to again, use our water product constant. And so then we get our Ka is 5.55. I'll round it to 5.6 times 10 to the negative 10. And then so now we have to compare, right, our tooth strengths. And so our Ka is related to our ammonium. And then, so which one is the bigger value? So you're comparing Kb versus Ka. So which one's bigger? So this is times 10 to the negative 11 on your KB. Yeah, so then it'd be the Ka is bigger. So so we're comparing this value to this value. Since this is the basic part, this is the acidic part. And then, so this is bigger. And so that means this is going to dominate and make the solution overall acidic. And so again, that's what it was saying here. So summarizing, so the Ka of ammonium is larger than the Kb of fluoride. So therefore, the solution is acidic. And so it turns out, too, you can ask Google. So I Googled ammonium Ka, and that could be another easier way to get there. And there'll be slight discrepancies in the value, but this one, so they're reporting ammonium. The Ka is 5.6 times 10 to the negative 10. So that's just what we calculated there. So either way, but again, just make sure you're looking then for the Ka value of ammonium, because this is your acidic portion. And then you could also, let's ask Google, I don't know if it'll give it to us, so Kb of fluoride. And so actually that does pull up something. Sometimes you don't always get that value that easily, but that's what you could ask Google, and it turns out it did give you the value. That's pretty similar to what we calculated. So we got 1.47. You know, again, I expect minor discrepancies depending on where you get your value, but again, you can tell that our acidic component is stronger. So does that make sense on that last one? Yeah, I probably won't ask you to do it on the exam, but at least, you know, try to take it in. That's a little tricky there. All right, so let's take a couple of minutes here. And so see if you can go through these salts. So do you think they're going to be acidic, basic, or neutral? We're just going to run and get some water so I don't die. All right, are we ready? Start going over these. So what do we think about A? So strontium chloride. Acidic, basic, neutral. So what's strontium derived from? What would it be the conjugate acid of? Hydroxide. So, well, so strontium hydroxide is a strong base. So then it disassociates completely. And so does that make strontium acidic, basic, neutral? So neutral. And then what about chloride? What do we say about that? So from HCl. And so then does that make it acidic, basic, neutral? So neutral. So excellent. So what's our overall classification? So neutral. Good start so far. So what about aluminum bromide? And that might be one of those tricky ones. So what did it say about aluminum? Yeah. So this was a weird one. I'm trying to find the statement. So remember there was like a statement here, if the salt cation is a highly charged metal ion, and so in this case our aluminum is considered a highly charged metal ion. And so what does that make aluminum then? Acidic, exactly. And so that's, again, one of those weirder scenarios. And so that means aluminum is acidic from our charged metal ion. And what about bromine? Where does bromine come from? So HBr, and then was that a strong acid, weak acid? So strong, so what does that make bromide? Neutral, excellent. And so that gives us overall acidic then. So this is a weird one. So did you guys figure out what the heck this is? Yeah.
Well, would it be in like 3 parts instead of just 2? Or
So let's rewrite it, and let's see if we can write it into 2 parts. So it has CH3, NH3, NO8. So at least what part do you think might be by itself for sure? What do we recognize on there? So NO3. So let's look at that. And then let's try to figure out what the heck this might be analogous to. So we know our NO3 is from our nitrate. And then if we look at this guy, so we can kind of see it should be a cation, right? So this has a -1 charge. This probably has a +1 charge. And then does this kind of remind you something? So nitrogen attached to 4 things. So does it maybe remind you of ammonium? So this is a tricky one. So this would be, it's analogous. So instead of having a hydrogen, it has a methyl group instead, so that CH3 is just a methyl, nitrogen, nitrogen, nitrogen. So that's what that looks like. And so this is, if you're curious, so this is called methyl ammonium. And so, you know, we may not know what methyl ammonium, what do you think its base is, though? If you're kind of comparing it to ammonium, you could draw it out too. Like, what would it look like, the base? Or do you think that the base, do you think it's weak, strong? What do we know about ammonium and ammonia? So we know it's weak, exactly. And so we can make the same assumptions about this then, that it's probably weak. And so we can presume that it's going to behave in the same manner, so with water. So just like the ammonium, right, loses a hydrogen. So same thing, this water can pluck up a hydrogen, and then we form this compound. Anyone know what this one would be called? Oh, you said what? I should give like 5 bonus points for whoever guessed this. Yeah. Got to be the druggie in the room. Yeah.
Would it still be methyl something? Methyl ammonia?
Close. What else could it be?
Methamphetamine?
Yeah.
It's a druggie, I went for it.
It would be the precursor to methamphetamine. You guys are killing me. So this is methylamine. So I don't know if y'all watch Breaking Bad, but like that was the compound that was in the train. Did any of y'all watch Breaking Bad? It was like probably the last show I watched. No, I'm joking. But yeah, so now methylamine is a highly regulated substance. And so it was made famous in Breaking Bad. They do like this whole train heist where there's a tanker car of methylamine and he replaces the volume with water or something. It was a lot of drama, obviously, for the TV show. But all that means is that methylamine is highly regulated. So, yeah. Anyways.
What is it typically used for?
Methamphetamine synthesis? I mean, I used to do like kind of this area of research. Like people like amines because they're good donors and they make nice like compounds. So people like to. Yeah, so you could do that, like attaching this nitrogen methyl group. So that's what makes. Yeah, and that's also, so the methyl group makes it more easier to cross the blood-brain barrier. So literally, right, amphetamine, like you just finished saying, is used to treat ADHD. So that's amphetamine. And then methamphetamine is literally the same thing. It just has a methyl group. Methamphetamine. I can't spell. No. How is it so hard to find methamphetamine? Why can't I spell? I'll just type meth. There we go. Somebody tell me. So literally the only difference. So you could start with like this sort of precursor and then attach methylamine on there. And that's like the most direct route. So hence why it's highly regulated. But yeah, literally that is the only difference, is one stupid methyl group. But because of that methyl group, it much more easily crosses the blood-brain barrier, which makes meth much more potent than amphetamine. And anyways, not to go on a rant, but this is why I never understand the drug classifications and why certain things are drugs and certain things are, naughty substances, because you could really cure your ADHD with meth, but obviously you'd want to take a very small dose of it compared to what you take for amphetamine. Anyways, dosage makes the poison, and so that's why. Anyways, we went on a huge rant about meth, but basically all we wanted to find out was that this was acidic then, since it could do that, so it makes our hydronium, again, just like ammonium, and so this salt would overall then be acidic. Okay, what about this last one? So NaCHO2. And so let's at least start with sodium before we try to figure out what this was. So what do we know about sodium? I think someone said neutral. So neutral, so again, that's from good old sodium hydroxide. So we know this is neutral. And then, well, let's say we're not quite sure what this is, but maybe we're looking for something H. Is that what they wrote? Yeah. So maybe looking for something HCHO2. So let's kind of see, is this a possibility? Ah, yes. So HCHO2. So that's our formula for formic acid. And so, yes, it is a weak base then, weak acid. So then going back to then, so this would be our formate ion. So then is our formate ion acidic, basic, or neutral? So what do we remember about our anions too? What are they always? If they're not neutral, then they are basic, exactly. And again, we see that, oh yeah, so our formate reacts with water, and then it would remake that formic acid, leaving us with hydroxide. And then this one, so that was just our example up here. And so what did we say this was? Ammonium fluoride. So acidic. And so that was just our example comparing our Ka of ammonium versus a Kb of fluoride. Okay, do we feel good about these? You're gonna be like, all I learned today was meth in class. All right, so our last bit is just kind of looking over the titration. So you did the titration in lab, and so like you saw, we had some sort of a solution of unknown titrant. So in this case, we're looking at the vinegar. Oh, I think I looked at it backwards. And so you just add your known concentration. So I feel like this is worded backwards. But basically you add whatever is in your burette slowly to whatever you're titrating. And then of course, like you saw, if you know how many moles you're adding, then you can calculate moles of whatever you're interested in. And so of course, we could tell the reaction is complete when we reach the equivalence point. And that was where, of course, the indicator told us we were at the equivalence point. So all that meant was the pH started shooting up. And that was where the moles of H plus equal our moles of hydroxide. And so y'all are at least vaguely familiar with indicators. And so with these different titrations, you of course want to pick an indicator that's appropriate. that would match whatever change you're looking for. So of course, in our case, we were just doing a simple acid-base titration. You had your vinegar here, dropping in your base, and then of course, once it reaches that equivalent point, it will change color. And then where is the graph here? So this is kind of our graph of what it would look like. So we were doing a weak acid versus a strong base titration. And of course, right, this is your pH of your solution initially, of your vinegar. And of course, imagine it with your phenolphthalein. And of course, colorless, colorless, colorless. And then notice how quickly it shoots up on that graph too. And of course, you guys saw that visually, right? It was nothing, 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 boom, and then oops, now you blew past it and it's dark pink. And so that's where, you're trying to get it as light as possible, so you're just right at that equivalence point. Of course, now you know that's much easier said than done. And so similarly, again, you would see this great jump in our strong acid versus our strong base. So of course, this starts off at a lower pH, and then it just shoots up once the base, again, overwhelms all your acid, and then we're at an extremely high pH. And so this is a weak base versus a strong acid titration. So you'd be starting with a weak base. And so notice with this weak base, you have a half equivalence point where your concentration of ammonia is equal to ammonium. And you could calculate this with your Haber-Bosch formula, or Henderson-Hasselbalch, that pH equals pKa plus concentration. And then your equivalence point would be there. And so this is more just so you appreciate it. So if you were doing like a polyprotic acid, then you would have two different equivalence points. So of course you do the first one, do all your equivalents. So let's say you were doing, sulfuric or even a triprotic. So this would be like so actually this is sulfurous acid. So H2SO3. And so of course, right, you have your first equivalent where you're just neutralizing the first set. And so then you have your first equivalence point. And this is where, right, you'd want to pick an appropriate acid-base indicator. So if you were doing like a polyprotic acid titration, you might have to pick, different indicators, or maybe one that changes several times. So for example, like thymol blue is always a good one, since it goes from red to yellow and then all the way to blue once you go basic. So this might be an appropriate one. Or you might have to use like 2 different ones or something. And so again, all these different indicators. So this, I'm not familiar with this one, alizarin. This would be another good one though for titrations, but usually people pick like thymol blue or phenolphthaleins. Those are the common ones. And of course the ones you've seen in lab, bromocresol green, that's another good one that people like. All right, I think we're pretty much done. Was there anything that we need to go over on the homework? So this one's pretty straightforward, just removing, your proton. So like carbonate would be your conjugate base there. Remove a proton, write ammonia for that one. And then so conjugate acids, you're basically just adding a proton then. So this one is water. This is HPO4 2 minus, so something like that. Trying to look at like the trickier ones. Oh, I remember what we should talk about. Okay, well, there actually is not a problem here that I was thinking about. All right, let's do 7, but then we're going to do 7 again. So we'll do what's the pH of this 0.1 molar sodium hydroxide solution, but then also answer, so what's the pH of a 0.1 molar calcium hydroxide solution? And how are they different? So take a minute, figure out the sodium hydroxide, and then figure out what's the difference with calcium hydroxide. So what do we get for the pH of sodium hydroxide? So how do we solve that? So what formula do we do? What can we solve? What were we given? So then if we know OH, so this means we have 0.1 molar concentration of hydroxide. So what could we maybe most easily plug it into? So negative log of what then? So which one does have hydroxide in it though? Because yeah, you're right, negative log thing, except what are we calculating then? Yes. So POH, and so this means we're calculating the POH then equals the negative log of our 0.1 molar. Oh. And now we're slightly out of time. And so this gives us, right, our POH, and so we could subtract to give us our pH now. So now we have our pH is 13. Now what's the difference in this one? And think back to your solution chapter 2. So what's the concentration of hydroxide ions for calcium hydroxide in this 0.1 molar solution? What did we have to do in our solution chapter? Remember when it disassociated? So do you remember how you multiplied it by the equivalence? So now this is saying, so we have a 0.1 molar solution of calcium hydroxide, except when it dissociates, right, we had 0.1 molar concentration of calcium, but then it's 2, I didn't write that very well, I'm sorry. Let's rewrite that. So write calcium hydroxide, so then you have 2 equivalents then of hydroxide, and so if it's 2, then that means you have a 0.2 molar concentration of hydroxide. So then the only difference, and I apologize since we're over time, so then you plug in the negative log of 0.2 to get your POH. And so that gives you a slightly lower number, and then 14 minus that gives you 13.3, which we expect since they would have a slightly higher concentration from those 2 equivalents. All right, so we are over and out of time. I am trying to enter in your quizzes too subtly, so if you want to come up and grab them, feel free. Yours I entered.
Okay, thank you.
I don't think I entered yours. Just let me. Here's yours. Let's see, these are the entered ones. Okay, yours is entered. Ben is entered. No. Izzy, yours is already entered. There's Ben. Izzy. Emma, yours has been entered. All right, now, so bear with me. Alessandro, Eric Carson, let me get you. Let me try to get the morning people.
Thank you.
Let's see, Abby, let me find yours. Okay, Joanna, you're next in line now. I didn't have time to alphabetize them. Yep. Yeah.
I can't find the lab. In my notes, I put it somewhere, but
You
the
couldn't.
last lab, I thought I turned it in on.
Oh, then I have them then. So I have all the labs that are ungraded. They're like sitting in labs, so you can reference them
Okay.
at least.
Sounds good. Thank you.
And then you got your quiz, right? Is Ashton, do you want your quiz? Let me put it in.
So the lab test is today,
Yeah.
and my calculator was working this morning, but between sometime this morning and today, it blew up.
It blew up.
Yeah, look.
Did the battery bust? Oh yeah, shit.
So what should I do? I don't have a calculator.
I could give you a calculator to borrow.
I can't believe it blew up. It was working this morning at
That's
10 a.m.
really upsetting. That it-
Yeah, I know. I turned it on and I was like, why would it not? And
Perfect.
so I was like, whoa, white powder.
That's awful. Who? Oh, Sonia's missing her quiz still. Oh, and Michaela. Sorry. I didn't put a score on yours apparently. And Sonia, sorry, let me enter yours in. And I think, did everyone get a quiz that took a quiz?
For these labs,
forgot to give you the one back from when I took German.
Oh, that's fine.
And then I accidentally took the reverse.
Um,
If it's open, I'm gonna put it back.
Yeah, it's not open.
Well, I'll be here for a while, so I'll
All right, yeah, I could also just take it. Got too excited, huh? And I at least entered them all now. Sweet.
There's that one that I showed you.